In this unit, we'll begin our discussion of conic sections. A conic is formed when a right circular double-ended cone with two parts, so that's this double-ended, which is the kind of cones you'll see in Calculus 3, is called a napes. And if we intersect this napes by a plane, there are different types of conic sections we can make. So slicing it by one plane, we can create this parabolic shape or a parabola. Slicing it horizontally, we create a circle. If we use a different angled slice, we create an ellipse. So a circle is just a very specific type of ellipse where the radius is the same all the way around. And an ellipse, we've got a minor and a major axis radius. Well, it's not really a radius at all. And then a hyperbola. So hyperbola, we've got these two very extreme or opposite pointing parabolic type shapes. You may remember from your English class, if you talk about hyperbole, hyperbole is an extreme situation or an extreme exaggeration, I should say. So hyperbolas, they're pointing to opposite extremes. So we're going to start talking about parabolas. A parabola is defined as a set of all points in the plane, equidistant from both a fixed line, the directrix, and a fixed point not on the line called the focus. When we consider the graph of parabolas, parabolas have an axis of symmetry. The axis of symmetry passes through the vertex and also the focus. The vertex is the midpoint between the focus and the directrix. And what that means is that this distance from the vertex to the directrix is the same as the distance from the vertex to the focus. So it's equidistant. That vertex is always going to be in the middle of these 2 points. Now, this directrix here, the parabola is never going to cross over the directrix. It's always going to focus its attention or wrap around the focus and be pointing away from the directrix. So the directrix, in a sense, gives us direction. It says, hey, we're going to move away from the directrix and about or around the focus. I like to think about focuses its attention around the focus. It wants to give the focus a hug. So let's look at the basic definition for a parabola. You all are now likely very familiar with a vertical parabola. So in algebra, our parabolas only opened up and down. But in trig, and as we explore conics, we'll have parabolas that open up or parabolas that open down, as well as parabolas that open to the left and open to the right. Here, we're going to discuss a vertical parabola. And this is a vertical parabola centered at the origin. So there are no shifts. Of course, we know that not all parabolas are going to be, opening up here and have that vertex at the origin. So they will be shifted later. But I think it's helpful for us to look at the definition without any shifts and then apply that or transform that to the transformation form. So in this example, our vertex is at the origin. And the directrix is identified as being y equals negative p. So p being some value. Y equals an equation. Y equals is a horizontal line at some negative value. So we have a vertex at 0, 0. And this parabola opens up. Now the focus is inside the parabola. Remember, I said that this distance between the focus and vertex is the same as the distance between the vertex and the directrix. So if the directrix is negative p units away, the focus is a point on the y-axis, which is positive p units away. So the focus is 0, p. And in this situation, the y-axis This vertical axis is my axis of symmetry. Now, if my p-value is positive, if it's a positive p-value, just like right here, the parabola opens up. But if my p-value is negative, that would switch these, and this would become a negative 0p, and that would become a positive y equals p. And that parabola would open down. The equation of a vertical parabola in standard form for our conic section is going to be x squared equals 4py. So now that we've discussed a vertical parabola, let's compare this with the standard equation of a horizontal parabola, which is centered at the origin. How is this similar and how is this different? So again, we're now looking at a horizontal parabola which is not shifted. That means the vertex is at the origin. Instead of this parabola opening up or down, it's going to open to the left or right. And of course, the right around our positive x-axis, that's going to be my positive value. Opening to the right is positive, opening to the left would be kind of a negative horizontal parabola. So the directrix is going to be behind the parabola over here on the left. The directrix is a line that the parabola never crosses. In this case, it's a vertical line, and that vertical line is going to be x equals negative p. That means my focus, which is inside the parabola, is on the x-axis, or positive p, 0. And of course, the x-axis, this horizontal x-axis, is my axis of symmetry. If that p-value is positive, that means we're going to move the positive direction on the x-axis. The parabola is going to open to the right. And of course, if we negated this p-value, the parabola would open to the left. So you see a lot of connections here, 0, 0. Instead of 0p, we have p0. Y equals negative p, x equals negative p. And then positive is up or to the right, negative is down or to the left for that p-value. And our form looks very, very similar here. It's y squared equals 4px. Now, I really like to encourage students not specifically to memorize, all of these formulas, but to recognize patterns. The patterns is what's going to make our life easier when we're working through these problems. So they're all very, very similar. It's just subtle differences. And as we work through this unit and we continue to talk about not just parabolas, but circles, ellipses, and hyperbolas, you're going to notice a lot of consistencies or similarities between all of these different standard forms. Let's do a couple examples with parabolas which are centered at the origin to kind of help you see what you might be encountering in the homework. Here, we're given a parabola. And of course, we know it's a parabola right now because we are in the parabola section. But as we move forward and we encounter these different types of conics, we need to be able to determine which type of conic it is that we're looking at. One thing we know is that ellipses, circles, and hyperbolas, they are all going to have both an x squared term and a y squared term. Now, we only have one squared variable, not the y squared. We only have x squared. And that's how I know this is a parabola, because it's not both x squared and y squared, again, like we'll see with ellipses, circles, and hyperbolas. Now, which type is it? Is it a vertical or a horizontal parabola? We have x squared, and x squared is a vertical parabola. So this parabola is going to be opening up or down, and we will determine that direction by considering the p-value. So we've looked at this, we've determined that we believe it's going to be a vertical parabola because there is an x squared term alone. We're asked to determine the focus and directrix. Again, skipping back, the focus and directrix both have a P in it. So we need to put it in standard form to determine what that P value is. My standard form here for a vertical parabola centered at the origin is x squared equals 4py. Clearly we can see we need that x squared term to be isolated. So if I look at rearranging this, I could multiply by -12 on both sides, and this similar equation would give me x squared equals -12 times y. X squared equals -12 times y. Now, we need it in the form of 4p. So I need a 4p here, and currently my coefficient in front of y is -12. Well, we can solve a quick equation, 4p equals -12, and we can very easily see that p is -12 over 4, or -3. So standard form is x squared equals 4 times -3y. Now that I have it in that form, I know that my p-value, again, is -3. And we need to think about what that means. So we have a vertical parabola. What does it mean when p is negative? That means the parabola opens down. So rather than just, again, reciting all of these details, I'm going to kind of sketch what we have. We have a parabola opening down. There's no shift, so we know that the vertex is at the origin. If p is -3, where is my focus going to be? It's going to be 3 units down from that vertex. So my focus is on the y-axis. It's 0, -3. And that means my directrix is a horizontal line 3 units up, and 3 units up, that gives me the horizontal line of y equals +3. So that is my directrix. And those are the pertinent or important pieces of information that we need to be able to state for this parabola. And of course, I didn't state, but the vertex is at the origin. Let's look at one more example in this video. For this example, we're asked to find the equation of the parabola. So we're told it's a parabola. We have a vertex at 0, 0, and a focus at 5, 0. So we want to determine the equation and then also graph this parabola. Well, I don't have a lot of information to go with here, but I like to try and visualize this. So my vertex is at the origin, 0, 0. And where is my focus? My focus is +5 units out on the x-axis. So my focus is in here at this point, 5, 0. Now, the p-value is always going to come as that distance between the vertex and the focus. In this situation, we can say that p is equal to 5. Now, is it a positive or a -5? Which way is my parabola going to open? Is it going to open around the focus or away from the focus? And of course, we know from what we learned previously that it opens around the focus. Because it opens to the right, we know that this is a +5 for my p-value. That means my directrix over here to the left is a vertical line. The equation of that vertical line is x equals, and how many units away is that going to be from the vertex? We are -5 units away. Now, of course, this isn't drawn to scale, but here is my graph. So I know my p-value is +5. It opens right. And my directrix is the vertical line, x equals -5. I do want to warn you, when you're graphing these on your homework, they want you to graph your vertex first, and then you need to pick another point. Sometimes you have to get a little bit creative in order to come up with that point, and using the equation can help you. So in this situation, we're asked to find the equation of the parabola. My equation of a horizontal parabola, we know that it's a horizontal parabola, is going to be y squared equals 4px, or rather y squared equals 4 times 5. P is +5. 4 times 5 gives me 20x. So this is my equation of the parabola. Now, outside of 0, 0, if I need to pick another point to plot, again, I might need to get creative. So I know I'm going to need to divide or multiply whatever that is times 20 to get that. And so I might think, well, I need a perfect square number over here. And is there a number that 20 goes into evenly? And the only perfect square number I can think of would be 100. So, for example, if I had this ordered pair, what happens if I let y equal 10? If I let y equal 10, then I've got y squared, or 10 squared equals 20x. That's 100 equals 20x. 100 divided by 20 equals x, or 5 equals x. So again, as I'm saying, when you graph, you're going to graph the origin. You need to come up with another point somehow. And the computer wants you to graph on those integer values. So just get a little creative to pick another point. All right? So that concludes parabolas centered at the origin, opening up, down, left, and right. So in the next video, we'll talk about parabolas which have now been shifted left, right, up, down, and they could also be stretched or shrunk vertically and horizontally.